Welcome back. We're going to be talking about sensation and perception in Chapter 5. So let's get started. All right, in my introductory slide, I am going to list all of the things that we're going to cover in this chapter. So we're going to talk about vision, we're going to talk about hearing, we're going to talk about smell, touch, taste, and then one that you maybe hadn't thought of as a sense before, but the sense of balance is the last thing that we'll talk about. So let's get started with a nice distinction between sensation and perception. It's really easy to lump these two together and think that they really are the same thing, but they are actually two completely separate fields of study. Sensation is solely interested in how the brain receives input from our sensory organs. So how the eyes carry light information up to the brain, how the ears collect sound waves, how the touch receptors in our skin collect information about different kinds of touch and convey it up to the brain, taste, smell, so on. So it's really about how the sensory organs work and how they then cast it up to the brain. Perception, on the other hand, is the field of study where we're interested in how the brain makes sense of the information that's coming up from the sensory organs. So it's really hard if you're interested in psychology at all to just solely talk about sensation, because you want to go right into, and then you mean this, you understand, you interpret. That's the field of perception. Sensation is simply the biological side of it. So I found this nice girl, woman, person on the internet, seems to be kind of excited about something, but I liked this photograph because she is showing us all of the sense organs in one picture. So obviously eyes, you can see ears, nose, tongue. That one's a hard one to find a picture of somebody where their tongue is showing too. And then of course all the skin receptors. All over your body you have skin receptors for collecting touch information. We talked about that in Chapter 2 when we talked about sensory neurons. So the sensory neurons are the ones that collect information from the skin. All right. Perception, on the other hand, is how your brain makes sense out of input. So if you look at this maybe with your eyes squinted a little bit, sort of look at this image and squint your eyes, probably the most obvious thing that'll pop up with your eyes squinted is a face. It's when you take a lot of the detail out, all that's left is the face. Now, if you look at it, looking at all the details, you'll notice that, oh, I see a woman in a long skirt wearing a fur coat walking across a puddle in the foreground. There's a tree even closer to us than she is, and bushes in the foreground also. Then there appears to be a field, and then in the background there's some kind of wall. There's an arched bridge or tunnel or something. And then in the far distant background, it looks like factories or apartment buildings or something. So you see all these details. But when you squint your eyes, the face emerges. The purpose of showing you ambiguous figures like this is to illustrate that depending on the angle, depending on the clarity, depending on a whole bunch of different factors, your state of mind, how far away you are from this object. I noticed when I was launching these slides, the thumbnail of this slide, all you really can see is the face. It isn't until you see more details that you can actually make out the lady walking across the puddle. The fact that different angles, different states of mind, those kinds of things cause us to interpret this picture differently really illustrates that your brain is trying to organize the information coming in from the sense organs into something that makes sense to your brain. So sometimes the conclusions that we draw might be faulty, which is really fun to study, the times that we make errors. Sometimes we go down the wrong path, but most of the time we draw correct conclusions. And that's why our perceptual system is really fun, is that it really, based on our previous experiences and other kinds of things, our perceptual system figures out what must be coming in from our sense organs. So that's what we're going to be talking about today. I'll spend part of each sense talking about the actual biology of how that sense works, and then I'll spend part of the time talking about how your brain makes sense of the information coming in from those sense organs. All right, so basically what we're trying to do is make sense of the world, right? We want to understand the things that are around us, that are coming in through our senses and stuff like that. There are two types of ways that we can impose meaning on the world. One is to just completely rely on the elements as they come in. We call that bottom-up processing. So when we have information coming in from our eyes, it comes in parts. Each receptor cell in your eyeball contributes a little part of the image, and your brain has to put it together, assemble it into a meaningful whole. The bottom-up part, the collecting of the elements, is really what the eyes are doing, collecting the little elements. That's called a bottom-up process. So sensation is a bottom-up process. You're just collecting the actual elements from the world. Perception is what we call a top-down process, where now you're going to interpret that information coming in from the sense receptors. So you're going to use models of what your brain has come to expect in the world, ideas, like whatever's in your mind right now, you're more primed to collect information that relates to it, or interpret information coming from your sense organs as if it's related to what you're already thinking about. You know, what you expect to encounter in a particular scene will influence your interpretations. So on the left side, I zoomed in on that picture, hoping that, you know, I'm in so close that you can only just really see the elements, and it's really impossible to figure out what it is. On the right-hand side, under top-down processing, well, now that you see the figure, maybe you're realizing that it's another one of those ambiguous figures, where it could be interpreted two different ways. It could be a mouse or a rat. You know, being a good psychologist, I see it as a rat, you know, with its nose pointing to the left, and you've got those circles serving as its ears, and then you see the tail swooping around underneath. Or you might be seeing a man's face, a man wearing round glasses. So now what had been the rat's ears are now the man's glasses, and that what had been like the curve of the rat's ear now looks like maybe the man's eye. The rat's whole head is now the man's nose, and what had been the rat's eye is now the, like, I don't know, wart or freckle or something on the man's nose. And now the rat's tail becomes the man's chin, and his hind leg becomes the man's ear. And clearly the man doesn't have any hair. Depending on your perspective, depending on which part of this figure caught your attention first, you may have seen a rat first, you might have seen the man first. It really is just a function of what your brain was expecting, and then it sort of guides your interpretation. I verbally explained where the different parts are just in case you saw one and not the other, so that you'd be able to say, oh, okay, I guess if I was in the right state of mind with proper explanation, whatever, I can see both. So top-down processing, we are imposing meaning on the information coming up from bottom-up processing. Okay, let's apply. So what do you see? Sorry, there's something on my screen. What do you see on this bottle? I'll let you ponder that for a second, because I'm sure you can't see anything, right? Most fully formed adults see two naked people, and they're both facing us, but one's in front of the other, and you can see frontal nudity of what appears to be a female in the front and what appears to be a naked male behind, but we're inferring that from the fact that we can see muscles and things like that. The woman has her arms around the man's neck up behind her, and he's like nuzzling her or something. Okay, so in case you didn't see it, that's what you might have seen. Would you be surprised if I told you that when they have shown this same picture to children, they see dolphins? You might have seen the dolphins, but in my classes, a lot of times students are like, what dolphins? So I put circles around all the dolphins. 8 to 10, depending on whether they count partial dolphins or if they notice all the dolphins, because one dolphin is swimming off of the side on the right side of the screen, down towards the bottom. So what's going on with that, right? Well, what you expect to see, you may have heard that old story about the alcohol ad that spells out sex in the ice cube. So you might have been kind of primed maybe that these kinds of images might contain something sexual. It might just be that you're much more familiar with seeing, you know, sort of sexual images rather than randomly placed dolphins all over. It might be that once we mature, we see sex everywhere. I don't know. I find that it's kind of fun to go back now. Because I'm sorry, for me, it pops right back into naked people, although now I also can see the dolphins. But to me, the dolphins are definitely secondary to the naked people. That shows you the role of expectation, experience, and those kinds of things as we impose meaning on ambiguous objects. All right. So here we have another ambiguous object. If we look at just the bottom-up process, what we see is black and white splotches, right? Some areas where it's more white, some areas where it's more black, and some areas where it sort of splotches all over the place. Now, if I tell you this is a picture of something that's been over-contrasted to the point where you can't really make out edges and things like that very well, you can start searching around and see, okay, well, what meaning can I impose on this ambiguous figure? Then if you're still struggling, I'm going to encourage your top-down processes by giving you some concepts. So maybe if I told you that there's a tree in this picture, I have to give you a little bit of a hint, though. The tree is not in its entirety in the picture. There's a tree there, you can see part of it, and then you really can see the shadow that it's casting. So knowing that might help you to start locating where the tree might be. There's a sidewalk, and even more specifically, it's an intersection of two very straight sidewalks. So there's a 90-degree angle where the two sidewalks intersect with each other. So you might be looking for that. When I give you hints, sometimes these sharp edges start to pop out, the sharp edges of the 90-degree angle. You might be seeing it. If I mention that the key figure in this photograph is a dog, maybe you're seeing it. I'll give you a hint that the dog is not facing us. He's walking away from us, sort of at an angle, so we can see his body, and he's got his nose to the ground. And if I mention to you that he's a Dalmatian dog, that might really help you to figure out that it's, going to be some of these splotches are going to come together and be the dog. All right, so hopefully by now you found the dog. But just in case not, I went ahead and I used my finger and paint, the paint program, and I tried to color stuff in so you'd be able to see it more readily. You should have seen my efforts to outline that dog, so please forgive his poor hind foot that looks like he's in a cast or something. But now that you see things outlined and colorized, it does make it a lot easier to visualize, right? But you might have already imposed that meaning. You saw it pretty easily. Once you saw it, you could see it, right? Once you impose that meaning, your perceptual system allowed you to see that object. That's how powerful it is. So even though it was completely ambiguous and other people, near you might have been saying, I don't see it, what are you talking about? Once you can see it, it becomes really obvious. So now that I've outlined it, let's go back to the blank uncolored version. And now that you've seen it, it's pretty easy to see where the tree is, the dog is, the sidewalks are, right? So those are good examples of how your perceptual system struggles to help you to make sense of the world around you, right? The information coming in through your sense organs. All right. The last thing I wanted to talk about in this segment is the concept of thresholds. So I always like to tell my students in class to tuck a pen behind their ear during this conversation. So if you want to grab one, you can. If you're already wearing glasses or headphones, you're already kind of doing this demonstration, so you don't need to tuck something extra in after. You'll understand what I'm talking about later on. So let's talk a little bit about thresholds. You've heard this term before. Back in Chapter 2, I talked about how input needed to exceed the neuron's threshold of stimulation in order for that neuron to have an action potential. We're talking about the same thing here. The information has to exceed the resting state for that neuron. In this case, we're talking about sensory neurons that collect information from our sensory organs. So there are two types of thresholds that I wanted to talk about. The absolute threshold is, brace yourself, the minimum stimulus intensity needed to detect it 50% of the time. So here we have someone getting a hearing test, and probably all of you have had a hearing test just to make sure that your hearing's working, basically. And what they do is they play sounds for you at different frequencies so that, they can kind of test whether you're losing some of your sensitivity in different frequency areas. And your job is to put your finger up whenever you hear the sound, or put your hand up whenever you hear the what they want to do is play that frequency of sound at the intensity level that will cause you to half the time recognize that it's there and half the time not. Then they will have established your absolute threshold. So how loud would I have to play this frequency for you to hear it just as often as you don't hear it? Now that term absolute makes it sound, absolute, like it would be consistent all the time, but it's not. Before I tell you about some of the things that can affect the absolute threshold, I wanted to mention subliminal stimuli. If you've heard about subliminal stimuli, which I know you have because I had you do the true-false test at the beginning of the class where I asked about it. But if you've heard about it, you might have heard that subliminal stimuli maybe can affect your shopping habits or prevent you from shoplifting while you're at a store or make you prefer one brand over another or something like that. As I mentioned in the true-false test, they don't work like that. They barely affect your attitudes for maybe 15 seconds, and that is not enough time to get your shoes on and your car keys and go buy something, that is for sure. But what the term subliminal stimulus means is that it is presented to us at below the absolute threshold, so that less than 50% of the time you notice it. So it doesn't mean that it's invisible. It doesn't mean that it's inaudible. It just means that you miss it more often than you detect it. So some subliminal stimuli are presented so quickly or so quietly that really you don't notice it. In research, we'll present a visual stimulus for like 5 milliseconds, and no one says that they saw it. But it can impact how they answer on the next question. So you're picking it up even if you're not consciously aware of it. So anything that you miss more often than you detect, we consider subliminal. Now, some people think subliminal means that it's subtle or that it's a marketing ploy. I mentioned earlier the alcohol bottle with the ice that spells out sex, and that's supposed to be a subliminal message because not everybody notices the word sex. The fact that it's there and static, like it would be in print ads. So clearly you could look at it and you could find it if you looked for it. That doesn't technically make it subliminal because it could be seen. Subliminal means it's been presented at a rate that's too quick or too quiet for us to detect it most of the time. So that's the important thing to kind of remember about that versus sort of just propaganda or other kinds of presentations. Okay, back to what I was going to say about how our absolute threshold gets affected by things. Competition in the same modality. So when you go in for a hearing test, they don't do it in the middle of the cafeteria at lunchtime. They do it in a quiet room because there's too much noise otherwise, and now it might be that you miss the noise not because you can't detect that intensity, but because something else was interfering in that same modality. So we would want to have a very quiet room if we're going to test your hearing. We'd want to have a dimly lit room if we're trying to test your ability to detect light. If you've gone in for a vision test, you'll notice that they turn the room lights off so that the only illumination is that array of letters, and you're supposed to name the letters, right? They turn everything else off so that we don't have a problem with competition in brightness. So competition in the same modality will raise the absolute threshold. So it'll take a more intense stimulus for you to be able to detect it, at least 50% of the time. So if I'm going to test your hearing in the school lunchroom, I'm going to have to give you much more intense stimuli, or put you in noise-canceling headsets or something like that. Distraction. If you're thinking about something else, it'll actually interfere with your ability to detect the information that's coming in through your senses. You've had this experience where you've been engrossed in something and somebody's calling your name. It's time for dinner and they're calling you, and you're not reacting at all because you literally are not detecting that stimulus. You're distracted. Your mind is on something else. Expectation. If you're ready for it, it will take a lower threshold stimulus for you to detect it if you're waiting for it to happen. If it's a surprising stimulus, it'll take a louder or a brighter or a harder slap or something like that for you to notice it, as opposed to if you're ready for it, it just takes a little bit of the stimulus. So you get a lower threshold when you're expecting it. And then how alert you are. When you're groggy, when you're tired, those kinds of things, it's going to interfere with your ability to collect information from your sense organs. And so you're going to need a higher threshold stimulus. You're going to need something that's louder, brighter, more intense. When you're sharp, really on top of things, it'll take less of the stimulus for you to notice it. There's another kind of threshold, the difference threshold. And this is looking at your ability to tell the difference between two very similar stimuli. So it's defined as the minimum difference needed to detect that difference with 50% accuracy. So how different would the two stimuli need to be in order for you to detect that they really are different from each other? We're talking about things like, are they different colors? Are those two tones different pitches? Do these two things weigh a different amount? You know, is this temperature colder than that temperature? Those kinds of things. Back in the day, Weber, who was German, established Weber's law for difference thresholds. And he said that stimuli must differ by a minimum percentage. He established that weights must differ from each other by 2% in order for you to be able to detect that they're different. So you might need an 8-pound weight and a 10-pound weight in your two hands for you to tell that they're different in weight. In fact, there was this big scandal a few years ago where they discovered that you might buy a set of 1-pound weights and they can differ by as much as an ounce, which means that you might have a 15-ounce weight in one hand and a 16-ounce in the other hand. You wouldn't notice it because it's within your difference threshold. They have to differ by 2% or you're not going to notice. I'd like to argue, does it really matter? But they were acting like it was a huge scandal that, you know, you might be underworking out or something. Light intensity must differ by 8%. Sound frequency, what determines pitch, must differ by 0.3% of a wave. So Weber very carefully quantified. He discovered on touch that it has one thing must touch your face at a different intensity that is equivalent to the weight of a bee's wing for you to know that somebody's touching your face. That seemed like a very imprecise measuring rubric there, but he tested everything and came to the conclusion that it's not that you have absolute thresholds for difference, but that they instead, the two things must differ by proportion. Now, I've been doing something on this slide to kind of illustrate the concept, and hopefully, you guys are watching this with a high resolution screen, so hopefully you're seeing the thing that I put on the slide that's different. In class, our projectors are pretty horrible, and so it's really hard to see the difference. But if you look straight down, vertically down the middle of the slide, you should see that on the left-hand side of the slide, it's literally one tick darker on the little color spectrum on the left than it is on the right. And you should be able to see that nice clear line going down the middle. But most of the time, people don't notice it because they just assume that it's sort of a variation on how slides can be reflecting or other kinds of things. And so none of my students in class can see it. I have to point it out to them because it's too subtle. It's not a big enough difference. I think here on my screen, I can absolutely see it, and especially once I pointed it out to you. So Weber's law tells us that things must differ by a steady proportion. Salespeople know this trick, and they know to sell. If you're coming in to buy something expensive, they secure that sale before they start pointing out that you need some additional things to go with that big purchase. So you go in and you buy a suit. It's pretty expensive. Once they've secured the sale, then they start saying things like, "Do you need it tailored?" Right? That usually they try and price tailoring at below Weber's law difference, so that you won't really notice. You're like, you know what? I do want it to look nice. I'll let your tailor do it for me. Or they'll sell you a shirt or a tie, or they'll sell you things to go with it, hoping that once you're adding these small things in, you won't really notice the difference in the total, right? If you're going from a $500 suit and adding on a $50 shirt, you might think, well, all my other shirts are going to look terrible. It's worth it. And you may not notice the difference. And so you're willing to spend that extra money. So here's another reverse way to put it. When manufacturers discount things, I mean, $1 off of Sunshine Flakes is a lot more noticeable and seems more worthwhile than $1 off of a shirt, right? Like, that's what you didn't even discount it. it needs to be bigger for you to notice the difference. So that's why they oftentimes report discounts in percentages, because they're hoping that that seems like a big enough percent for you to make it worthwhile. So 10% off sunshine flakes, 10% off the shirt. Now we're talking about things that are comparable. All right. Okay. So if you put your pen behind your ear, it's time to ask you, do you still feel it? Most of the time, unless it kept falling out and you had to struggle with it, which happens, you probably got used to it and forgot you even had it back there. Those of us who have glasses on or headphones on, things like that, you didn't need to add a pen because you already experienced sensory adaptation. You get used to it. You just start ignoring the stimulus. So look at the blue dot here and try not to move your eyes. You're welcome to blink, things like that, but just don't move your eyes. Just keep looking at that blue dot. So we're watching a field of greenish-yellow birds flying across a background of reddish-orange background while staring at a blue dot. Very stimulating lecture. It'll be worth it a while in a second. It's surprising how long 30 seconds takes to pass. There you go. Now you got the blue dot on a white background, and now what do you see? For most of us who have working color receptors, we see a blue field and pink birds that slowly fade out of shape until pretty soon we go back to just a blank white background. So that was an example of sensory adaptation also. So let's talk a little bit about sensory adaptation. Your sensory receptors stop collecting information when they get accustomed to that constant stimulation. So I had you stare at that dot for a full 30 seconds to convince your color receptors that it was going to be unchanging. You might as well just relax because this is what we're going to be doing. And so they stop responding to those colors. So the original colors were like a greenish yellow and then on a reddish orange background. You saw the opponent colors when we went to a white background because your color receptors in those patterns got adapted so that the greenish yellow receptors, when I switched to white, were like, I'm not responding to this anymore. Hey, wait a second, it's changing. I got to wake up. I got to start firing. Because for you to detect solid white, you need all your color receptors firing together. So when you have some of your receptor cells having adapted to a certain color, when you see white, you'll notice that adaptation has occurred because you'll see the opposite color of what you had been looking at. And we'll talk a little bit more about opponent processing and stuff like that later on. But that's the basic premise, is that your color receptors adapted to that constant stimulation that I exposed you to with that picture. All right. This is a good time to stop. We'll come back in our next segment. We'll start talking about perceptual set and then vision.